Consider binomial probability. And we're going to start by discussing what is called a Bernoulli trial. This is an experiment with exactly two possible outcomes, one of which we'll call success and the other we will call failure. The probability of those will be P and Q. P for success and Q for failure. Notice they're complements of each other, and so if we know the probability of success, all we have to do is subtract from 1 to obtain the probability of failure. Many times, if you have an experiment with several outcomes, you can rephrase it as a Bernoulli trial, in which we only have two outcomes, success and failure. So here, if we look at our usual sample space here, if we roll a single die, our sample space will be the numbers 1, 2, 3, 4, 5, 6, and so our probability of obtaining a 5 will be 1/6. This is what we're going to call the probability of success. We'll call it lowercase p. Probability of success will be 1/6. Therefore, what is the probability of failure? 1 minus 1/6. Let me write down that this is the probability of failure. So this will be 1 minus 1/6, which is 5/6. So instead of our dice experiment having the usual 6 outcomes, all of which are equally likely, now we have 2 outcomes, and those probabilities are not the same. We have success and we have failure. Those are the only 2 outcomes that we have. Let's suppose that we roll a pair of dice. We're going to consider success to be rolling a sum of 7, 11, or 12. Okay, so my sum is 7, 11, or 12. In order to calculate the probability of this occurring, we have to go back to our equally likely sample space, which consists of 36 ordered pairs. We have to determine which of these fall into our event. So our event is going to be, first of all, let's get a sum of 7. So that can be done by doing 1/6 or 6/1. Let's try 2. So 2, 5. Or 5, 2. And then we can also do 3 and 4 in either order. These are all the ways that we can get a sum of 7. How can we get a sum of 11? We could do 5, 6, or we could do 6, 5. And there's only one way to get a sum of 12, and that's the ordered pair 6, 6. And that's our event. How many are in our event? We're going to need that because we're going to count those and divide by the number in the sample space, which is 36 ordered pairs. How many in our event? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 36, which is 1/4. That's our probability of success. Therefore, our Q, or our probability of failure, is 1 minus 1/4, which is 3/4. Okay, now we're going to consider what happens when we repeat a Bernoulli trial several times. And we're going to discuss the probability of a particular number of successes. Okay. Let's let S represent success, and let's let F represent failure. So we're going to repeat a Bernoulli trial 6 times, and each time the trial is independent of the others. In other words, our probabilities will not change. Our probability of success will be P. Our probability of failure will be Q. So from the multiplication principle, since they are all independent, success, failure, success, 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 and then failure. since they're all independent, that means that we can multiply the probabilities for each of them together. In other words, we can multiply the probability of success times the probability of failure, probability of success, probably 3 successes in a row, and then a failure. So this will be P, and then Q, and then 3 P's in a row, and then another Q. Since these are just numbers and we can multiply them in whatever order, that gives me P to the 4th Q squared. Okay, what if I have 3 successes, then 2 failures, and then a success? So this time I'm going to have P times P, and then Q, and then another P. So once again, I get P to the 4th Q squared. Notice the same answer as before. So now, what's the probability of having 4 successes in 6 trials? Well, what we need to do is figure out how many ways are there to take 4 successes and distribute them among 6 trials. So this will be like choosing 4 of our 6 trials to be successful. Okay, so that'll be combination 6, 4. We have 6 trials. We're going to choose 4 of them to be successful. So the probability of 4 successes in 6 trials will be, we know that we have P to the 4th Q squared each time, but now we have to multiply that by the number of ways to distribute the 4 successes among the 6 trials. So the probability of 4 successes is equal to combination 6, 4 times P to the 4th times Q squared, which is 15 P to the 4th Q squared. Okay, at this point I'm writing it in terms of P and Q because we haven't chosen a specific number for P and Q. I'm just trying to show you how this works, putting them together. Now if we look at a single die and we roll it 6 times, so here our probability, we've already looked at this, our success is we roll a 5, and that'll be on just one trial. So on one trial, getting a success would be getting a 5, and so the probability of that happening will be 1/6. Therefore, the probability of failure will be 5/6. They must add up to 1. So our probability of getting 4 5s, and let's let x, we call this a random variable. When it can, x is a random variable if it represents a number. Okay, so let's let x represent the number of successes. This will just help us have a notational system in which we can write down our numbers of successes. So here we're going to write the probability of getting 4 successes, meaning the probability of our number of successes is 4, is going to be combination 6, 4. So we have 6 trials. We're going to choose 4 of them to be successful, multiplied by, here's what we do. We have P to the 4th Q squared. We just did this little calculation above. So we end up with 15 times 1/6 to the 4th times 5/6 squared, which is approximately 0.00804. That's the probability of getting 4 successes in 6 trials. This leads us to a more formal description of this. This is what we call a binomial experiment. A sequence of experiments is called a sequence of Bernoulli trials, and we call that a binomial experiment. If the same experiment is repeated a fixed number of times, only 2 outcomes are possible in each trial. That's what we're going to call success and failure. The probability of success on each trial is a constant. In other words, the probabilities do not change from trial to trial. All the trials are independent. And the result of one trial does not affect the next. Here's the formula that we really just did. The probability of success is P, and the probability of failure is Q. And then the probability of having exactly X successes and N trials, combination NX. So what we do is we take the total number of trials, we choose X to be successful. Then we take the probability of success, raise it to the number of successes. Then we take the probability of failure, raise it to the number of failures, which we can get by taking the total number of trials N and subtracting the number of successes. The reason we call this a binomial experiment is because the formula should remind you of, if you've seen it before, the binomial formula, which is what we get by if we take that should be a plus, if we take a binomial and raise it to the nth power, we end up with a formula that looks like this. Notice each of our terms in our formula look very similar to the one that we just had. You don't need to know the binomial formula for finite math, but if you've seen it before, the pattern of this should look familiar. In each term, the sum of the exponents should be equal to your total number of trials, or in this case, the total exponent on our binomial. And so that's the reason for the name binomial experiment. Let's do another example. Let's go back to our die. And this time we're going to roll our single fair die 10 times, and we want to figure out the probability of exactly 3 fours, at most 3 fours, and at least 1 4. So what we need to do here is we need to decide how we're going to define success. So here, success is going to be I roll a 4, and that'll be on one trial. In other words, we're going to look at each trial separately. We're going to think of it as 10 small experiments inside our one big experiment. So on one roll, what's the success? Is I roll a 4. And so what's the probability of success? 1/6. And so the probability of failure then would be 5/6. And then we're going to let X be the number of successes in 10 trials. So for A, we want to figure out the probability of getting exactly 3 fours, or exactly 3 successes. So I'm going to label this as probability that X is equal to 3. Number of successes is equal to 3. So now what I do is I do a combination. I've got 10 trials. I'm going to choose 3 of them to be successful, so combination 10, 3. Then I'm going to take the probability of success, which will be 1/6, raise it to the number of successes. So if that's the probability of success, how many successes do I have? 3. Now I take the probability of failure, which is 5/6. The exponent on this one will be the number of failures. If I have 3 successes in 10 trials, how many failures do I have? 7, because I have to have 10 altogether. Notice these two exponents, the 3 plus the 7, adds up to the number of trials. So we should end up with 0.1. 155. Make sure that you work this on your calculator and that you get comfortable doing this arithmetic on your calculator and putting it with the combination 10, 3. Make sure that you can duplicate these answers. Let's move on. Let's determine the probability of having at most 3/4. So that means up to 4 successes. So the number of successes will be less than or equal to 3. We're going to have to do each of these separately. Our formula only gives us the probability for having a fixed number of successes. And so here we're going to have several possibilities for the numbers of successes. So it's possible we get 0 successes, and it's possible we're going to get 1 success. So we're going to figure out the probability of 0 successes, then we're going to add it to the probability of 1 success, add it to the probability of 2 successes, add it to the probability of 3 successes. Because 0, 1, 2, or 3 are our possibilities. For each of these, we're going to have a separate formula. So here we're going to have combination 10, 0. We're going to have 10 trials. We're going to choose 0 to be successful. Then we're going to have 1/6, raise it to the number of successes, which is 0. And then 5/6, raise it to the number of failures, which would be 10, right? Now we do combination 10, 1. 1/6 to the number of successes, so 1. 5/6 to the number of failures. If we have 1 success, that means we're going to have 9 failures. Next, now we've got 2 successes, so we take the 10 trials, we choose 2 to be successful. Then we're going to have 1/6 raised to the number of successes, so 2. 5/6 raised to the number of failures, so 8. Next, we have 10 trials. We're going to choose 3 to be successful. 1/6 raised to the number of successes, so 3. 5/6 raised to the number of failures. This is actually this last term is the same calculation we did in part A. Now you want to notice a few things here when you're punching things in. Combination 10, 0 means we're going to choose 0 of the 10 to be successful. That means they're going to choose the whole entire group. How many ways can that happen? Just 1, right? And what's any non-zero number raised to the 0th power? Also 1. So you want to save yourself a little bit of time by not punching in combinations when you don't have to. What's combination 10, 1? How many ways are there to choose 1 out of a group of 10? 10. So you can just punch in 10 there. And then the others will be exactly what we had before. I'm just pointing that out so that you can be a little more efficient when you're punching things into your calculator. You should get about 0.9303. Be sure that you pause the video and duplicate this on your calculator. It's an involved calculation and it's not difficult, but it takes a little bit of practice to make sure you don't make any mistakes with the parentheses or anything like that. So you just want to make sure that you're comfortable and accurate in doing that. Let's move to the next part. Here we've got to determine the probability of getting at least 1/4. So we need the probability of 1 or more successes. Okay, so what are their possibilities then? We could have exactly 1 success. We could have exactly 2 successes. We could have exactly 3 successes. We could have 4. You see the pattern here. How far up are we going to have to go? Well, we have 10 trials, so we're going to have to repeat this all the way up until we get to 10. For every single one of these, you're going to have a separate formula that you have to calculate. So this will be rather tedious. When you see something like this, you want to ask yourself if it will be easier to work with the complement rather than the event. In this case, it will. What is our complement then? our event will be at least one success. So what's our complement? 0 successes. That's going to only be one formula to calculate. So the probability of x equals 0. Okay, so we do combination 10, 0. So we have 10 trials. We're going to choose 0 to be successful. Then we're going to take the probability of success, 1/6, raise it to the number of successes, which is 0. Probability of failure, 5/6, raise it to the number of successes. Sorry, number of failures, which is 10. Each time you take the probability of success, raise to the number of successes. Probability of failure, raise to the number of failures. So you should get about 0.1615. And so now what is the probability of getting at least one? Well, if our event is we get at least one success, then our complement is we get 0 successes. Anytime we want to figure out the probability of the event from the complement, we subtract from 1. So that means we're going to take 1 and we're going to subtract the probability of getting 0 successes. So we take 1 and we subtract that 0.1615 that we just found, and so you should get 0.8385. In the U.S., about 9% of people have blood type B positive. If 20 people donate blood, we want to determine the probability that exactly 3 of them are B positive, and then we'll do at least 3. So first of all, we need to define success. Even before that, we should notice that this is a binomial experiment. We have a repeated number of trials. We can consider each person to be a trial, and therefore the number of trials here is 20. What is the probability of success? Well, first of all, what is success? We're going to define success to be that person has B positive blood. And so the probability of success then will be 0.09 because 9% have blood type B positive. Then what is the probability of failure? We simply subtract from 1, so that'll give me 0.91. And we'll let x represent the number of people number of successes in 20 trials. In other words, the number of B positive people in our 20 trials. Okay, so we're going to tackle this in 2 parts. Let's look at the exactly 3 being B positive first. We'll call that part A, and then we'll call this other part B. So here in part A, we want to figure out the probability that exactly 3 are B positive. So that means our number of successes will be exactly 3. So when we do our formula, remember we'll start by doing a combination. We'll choose out of the 20 trials, we will choose 3 to be successful. Then we'll multiply by the probability of success raised to the number of successes. And then the probability of failure raised to the number of failures. 20 trials, 3 successes, therefore we have 17 failures. You should get about 0.1672. Okay, let's move on to where we have at least 3 being B positive. Okay, so here we want the probability of at least 3 successes. We're going to have a separate formula for each possible number of successes. So that means we could have 3 successes. We could have 4. We could have 5. All the way up to the most we could possibly have would be of the whole group. Every single one was successful. So we would go all the way up to 20. So we're going to have a whole bunch of formulas to add up. For each of these, we're going to have a separate formula. And so we don't really want to do this. We want to use the complement. You want to look and see if the complement will make your life easier. And in this case, it definitely will. So if my event is at least 3, then what is my complement? Less than 3, right? In other words, what we want to find is the probability that we have less than 3 successes. And so what are our possibilities? We could have 0 successes. We could have 1 success. Or we could have 2 successes. 3 we don't want to include because that's in the event and we're just looking at the complement. So now for each of these we're going to have our formula. So here we're going to have combination 20, 0, which means we're just choosing the whole group. We're not laying aside any of them. So that'll just be 1. Probability of success, 0.09 raised to the number of successes, 0. Probability of failure, raised to the number of failures. If we have 0 successes, that means we must have 20 failures. Next, we're going to have 1 success. So that'll be combination 21. Remember, that'll just be 20 because there's 20 ways to choose 1 out of that group. And then we have 0.09 to the first and 0.91. If we have 1 success, we must have 19 failures. Then we do it for 2 successes, so this time we will need our combination. Combination 22, and then 0.09 to the 2, 0.91 to the 18th. Put all this into your calculator. You should end up with approximately 0.7334. Now, how do we calculate the probability that we want? Our probability that x is at least 3, we're going to do 1 minus the probability of the complement. So we're going to do 1 minus that answer that we just calculated, which is about 0.2666.